energetics for bond enthalpies. The essential idea: energy is absorbed when bonds are broken and is released when bonds are formed. Nature science, models and theories. Measured energy changes can be explained based on the model of bonds broken and bonds formed. Since these explanations are based on a model, agreement with empirical data depends on the sophistication of the model, and data obtained can be used to modify theories where appropriate. Breaking and making chemical bonds. The balloon in these diagrams is filled with hydrogen gas and then lit with a candle on a meter stick. You can see the balloon here. It is set alight and it explodes in a ball of fire. I want to have a think, based on chemistry, 2 things that you know for certain about this reaction. And I want you to suggest a reason for the type of observed enthalpy change. Press pause and have a good think about that. And we're going to go through this now. So what is happening in the chemical reaction? Well, you've got hydrogen gas, and it's obviously reacting with oxygen gas in the air, and it gives us water vapor. And it's an exothermic reaction. There's heat given out, isn't there? We know that bonds in reactants break, and we know that new bonds form in the products. And we've also already learned that energy is needed to break bonds, and the energy is released when bonds are formed in products. Most chemical reactions involve breaking bonds and then making new bonds. Energy enters the reactants to break the bonds, and energy is given out when the bonds are formed in the products. So bond breaking is endothermic, bond making is exothermic. Endothermic reactions. The energy in to break the bonds is greater than the energy out when new bonds form. The energy in is greater than the energy out. So the energy needed to break the bonds is greater than the energy released when the bonds form. Therefore, the energy is absorbed overall in endothermic reactions. In exothermic reactions, the energy in to break the bonds is less than the energy out when new bonds form. The energy in to the system is smaller than the energy out. So the energy needed to break the bonds is smaller than the energy released when the bonds form. Therefore, energy is released overall. What does this look like on an enthalpy diagram? Well, let's have a look here. We've got the enthalpy on the y-axis in kilojoules. We've got reaction progress or time. We've got reactants here. And we know that the products in an endothermic reaction have higher enthalpy than the reactants. And so, first of all, energy is used to break the bonds. Then energy is released when new bonds form. And the difference between the reactants, the enthalpy reactants and enthalpy products, is going to be positive in the endothermic reaction. The energy needed to break the bonds is greater than the energy released when bonds form. And let's have a look at exothermic. The reactants, the enthalpy of reactants is greater than the enthalpy of products. The energy used to break the bonds is smaller than the energy released when new bonds form. And you can see here that the change in enthalpy is exothermic. It goes between the enthalpy of reactants to the enthalpy of products. The energy needed to break the bonds is smaller than the energy released when bonds form. Bond enthalpy refers to the energy required to break 1 mole of a given covalent bond in a molecule under standard conditions. All reactants and products are in a gaseous state. Here we've got chlorine gas, and you can see the chlorine-chlorine bond here being broken to give 2 chlorine gaseous atoms, and the enthalpy change 2 for 2. So the bond enthalpy for the chlorine-chlorine bond 2 for 2. Here you've got oxygen, and the bond between the oxygen atoms is broken, the double bond, to give 2 gaseous oxygen atoms, and the bond enthalpy is 498 for that oxygen-oxygen double bond. Most types of bonds are found in different molecules or chemical species. Look here, we've got water. There's the oxygen and 2 hydrogens. The first OH bond's broken here, and it gives us the bond enthalpy for that is 502 kilojoules per mole. Then if we break the second bond, we'll get a bond enthalpy of 427. So they're different bond enthalpies. If we have a look at methanol, it's got 1 OH bond, and the bond enthalpy for that oxygen-hydrogen bond in methanol is 424. So we've got 3 different bond enthalpies there for the same bond, for the same oxygen-hydrogen bond. So the average bond enthalpy for OH bond, based on many types of molecules, is giving us 463 kilojoules per mole. Bond enthalpy is the energy required to break 1 mole of a covalent bond where all reactants and products are in the gaseous state. It is the average energy used to break that bond in a range of different covalent molecules. Let's have a look at that more closely. There's a lot going on there. So bond enthalpy is energy required to break 1 mole of a covalent bond, and it must be in the gaseous state. It's the average energy, okay, to break that bond in a range, taken from a range of different covalent molecules. The bond enthalpy values can be found in table 11, and you can see you've got, say if you want to find the bond enthalpy of, I don't know, carbon and chlorine, you just go along and you could find it there. The double bonds, triple bonds, etc. are given below. Forming a bond releases the same amount of energy as that used to break the bond, which kind of makes sense. So here you've got hydrogen gas giving 2 hydrogen gaseous atoms, and that's plus 436, so you can probably guess that the bond is endothermic because you're breaking the bond. If you're to form a bond, it's going to be exothermic, and it will be the same number but negative, and we know the bond formation is exothermic. The bond enthalpy values can be used to estimate the energy needed to break the bonds in a reactant and the energy released when bonds form in the products. Let's have a look at the energy required to break all the bonds in methane. So we've got CH4 giving us a gaseous atom of carbon and 4 gaseous atoms of hydrogen. The energy required would be 4 bond enthalpies of carbon-hydrogen bonds. It would be 4 times 4 and 4, giving us 1656 kilojoules. And we're breaking bonds, so it's going to be endothermic. Energy released when bonds form in water, you've got 2 hydrogen atoms and oxygen atom coming together. There should be a gaseous thing there, shouldn't there? To give gaseous water. The energy released will be 2 oxygen hydrogen bond enthalpies for oxygen and hydrogen, which is 2 times 463, giving us 926. And we know it's exothermic because bonds are being formed, and it's minus 926 kilojoules. The enthalpy change equals the energy used to break bonds minus the energy released when bonds form in a reaction. So we can use bond enthalpy values to estimate the enthalpy for reactions. Let's have a look at these reactions for hydrogen and oxygen giving us water. I'm just going to write that formula at the top there to remind us. So we've got 2 hydrogen molecules and an oxygen molecule, and we've got 2 water molecules and products. So we've got 2 bond enthalpies for hydrogen and 1 bond enthalpy for the oxygen double bond. Do the math and you get the endothermic part of the bond enthalpy of the reaction. Then we can look at the products. You've got 4 bond enthalpies for oxygen and hydrogen, multiplied by 4. We get the exothermic part, and you take away the bond enthalpy of the products from the reactants to give us an overall exothermic reaction with a bond enthalpy of minus 482 kilojoules. Another example, we can use bond enthalpy values to estimate the enthalpy change of combustion of propane. There's the balanced equation. There's propane. We've got 5 oxygens. We've got 3 carbon dioxides. We've got 4 waters. Oops, sorry. So we've got 2 carbon-carbon bonds there. That's 1, 2. We've got 8. 1, 2, 3, 4, 5, 6, 7, 8 carbon-hydrogen bonds. We've got 5 oxygen-oxygen double bonds. Put in the bond enthalpies from the data table, and you can get the energy required to break those bonds. And then look at the products. We've got 6 carbon-oxygen double bonds, and we've got 8 oxygen-hydrogen bonds. Look them up, and you can find the energy released when those products are formed. And then we can take away the energy of those products from the energy, the bond enthalpy of the reactants to give us minus 2034 kilojoules. Why is the change in enthalpy value calculated using bond enthalpy values only an estimate? And we've got to remember this, it is only an estimate. Well, let's think back to the definition of bond enthalpy. And under the conditions, what do we want? Well, we know that the reactant products need to be in the gaseous state, and we know that the average of all bond enthalpies in a range is taken from the average of all bond enthalpies in a range of molecules. Okay, these are the values. Well, the actual reactants and products may be a solid or liquid that you're looking at in a reaction, and so kinetic energy will be lower, so the enthalpy will change in reality. And the actual bond enthalpy for the given reactant or products may be higher or lower than the average value. Furthermore, additional energy is required to break intermolecular forces in liquids and solid reactants. Okay, so these things mean that it is most certainly just an estimate when calculating using bond enthalpies. Splendid.